3, 2, 1, let's go! Hi everybody and welcome to another exciting edition of Boring JavaScript. I'm your host, the Virtual White, aka Mike Smith, and today we're going to be talking about typed arrays. Now basically typed arrays gives you the ability to associate different values within a binary data stream. For example, if you were to load in a JPEG file, that JPEG file has different markers within its binary storage that says, hey, this is a JPEG file, this is how big this file is, this is the compression algorithm used, and so on and so forth. Well, typed arrays allows you to say, hey, these two first bytes is going to be an unsigned integer, this might be a floating point number, this section right over here might be a string. And it allows you to be able to associate those particular pieces of that data stream with actual variables within your JavaScript that you can then parse, use, and do whatever you want to with it. Want to see how it works? Well, let's get started. Now, all typed arrays work exactly the same way. It just depends upon what type of information you want to return. So let's take a look to, first of all, at one particular one on line 3 here and break that one down, and then I'll just go through all the rest of them very quickly. First of all, type arrays only work on array buffers. So I have a function here that I've built called build buffer, which will return me an array buffer. In fact, if we go down to the function itself way down here, here is my new array buffer. All of these typed arrays work on an array buffer and will access this array buffer to be able to say, okay, I need to get whatever information I need. So everything will always work on an array buffer. Just want to make sure you're aware of that. So I've got my array buffer being built up here. And let's take a look at this very first one here and kind of explain what's going on, because all the rest of them will work the exact same way. To be able to create the typed array, we initiate it with a new construct, because all of these are just basically classes. So we instantiate it with the new with the new keyword, and we pass it 3 different variables. We pass it first of all we pass it the buffer that we're going to be working with, because obviously it's got to point to some sort of buffer. What byte to start with, because remember this is a binary byte array. In this case, I've got 256 bytes, so I've got to, be able to tell it where to start with. It's at byte 0, byte 10, byte 100, or whatever, and then the length of the array to return. So in this particular case here, I am going to return a 8-bit integer array. That's what the int 8 means. It basically means an 8-bit integer array. And 8 bits is a byte, so it's 1 byte apiece, and my buffer is 256 bytes. So I'm going to return an array of integer numbers, which will be between -128 and 127, from buffer starting at byte number 0 with a length of 10. And that means basically when that finishes up here, it's going to take those very first 10 bytes and it's going to return inside the int 8 array here the 10 values of the first 10 bytes there. So int 8 array will give you 8 bits in an integer format, in this case starting at byte number 0 for a length of 10. And all the type arrays are going to work exactly the same way. So if I would go to this very next one here with the uint 8 array, this gives me an unsigned integer, which is 8 bits long. In this case, that's going to give me a number between 0 and 255. And again, I'm doing 10 of them here. This is going to be what we call a clamped array. Now, what's the difference between an 8-bit clamped array or just a regular 8-bit array? An 8-bit array, if you were to physically set the number, let's say to 256, which is not a valid number, what's going to happen there is that the array is basically going to say, okay, well, that's 256. We're going to actually take the modulo of that, so we're going to actually put the number 0 inside there. Or if you try to put the number 257 in there, it's going to put the number 1 in there because it's just going to modulo itself. If you think about that, it's going to divide it by 256 and give you your remainder. That's what's actually going to happen within a regular array. But within a clamped array, anything below 0 will always get set to 0, and anything above 255 will always get set to 255. And in fact, when I'm doing my build buffer down here, I really didn't have to, but just for the heck of it, I went ahead and used the clamped array because I wanted to make sure anything above 255 was always 255. In reality, I didn't have to do that, but it doesn't really matter. So the clamped array gives you 8 bits of an unsigned integer number. Again, that'll give you a number between 0 and 255. The int 16 will give you a 16-bit integer number. 16-bit is 2 bytes long. And that will give you the integer number. That will give you between negative 32768 and 32767. And I got my list over here on my other monitor, so that's why I keep looking over there. I don't have these numbers memorized. uint will give us an unsigned integer of 16 bits. Again, 2 bytes. That will give us between 0 and 65,535. The int32 array will give us a 32-bit number. That's 4 bytes long, not 8. That's 4 bytes long. That'll give us a number between, what is that, negative 2 trillion or something? I don't know. Doesn't really matter. You can figure it out. Don't worry about that. Unsigned integer will give us a 4-byte unsigned integer array. Float32 will give us a floating point number, an IEEE floating point number that is 4 bytes long. Float64 array will give us a floating point number that is 8 bytes long. Big int 64 array will give us a big integer, and the big int is a data type that's fairly recent to JavaScript. That will give us an you take up 8 bytes per number. That will be a signed number, and an unsigned big int will give us again 8 bytes, of a number. And each one of these is going to go 10 here, but as you can tell, each one of them I am starting with 0, which means that you can associate typed arrays, that you can associate different type arrays with any point on the array buffer itself. So every one of these are starting at 0 and giving me how many other bytes it needs to be, anywhere from 10 bytes here to 80 bytes here, since that's 8 bytes apiece. I'm just associating everything pretty much at the same site. So you're not limited to say, okay, well, this is going to be a 2-byte number. It's always going to be a 2-byte number. No, if you need for some reason for it to get to 2 individual bytes, just do uint 8 array. Boom, and you've got them. And then I'm just going to console log out to show you what the output's going to be, and it's going to be a huge mess. So let's go ahead and take a quick look at that. Let's flip over to Node. And let's type in node typed, let's spell that right, yeah, typed array. And we got a giant mess here, but here's my int array, here's my int8 array. Works out great. Here's my uint array. Notice that here it interpreted these numbers which are above 128 to be negative, which means the integers did work. Here's our clamped array. That should be exactly the same as our uint array. Here's our 16-bit numbers right here. Here's our 32-bit numbers, and I'm not going to pronounce them. Here's our floating point numbers for 32-bit. Here's our floating point numbers for 64-bit. Here's our big int 64s and our big unsigned int 64s. So as you can tell here, I just took the same values starting at number 0, at byte number 0 here, and just associated with different numbers. So type arrays, you can do anything you want with it and associate the values within any part of the array buffer. So next, what we're going to take a look at is show you how to combine all those to be able to describe a data structure. That's next. So next, let's take a look on how typed arrays can be used to define a structure within an array buffer. So what I have here is kind of a sample that I threw together of, let's say, some header information of an array buffer. Let's say we've downloaded a binary file, and that binary file has some sort of header at the very beginning. And that header happened to be a 16-byte header, and it said, well, the first starts with an unsigned word, then we have an unsigned byte, then we have a signed byte, then we have 8 characters for the title, and then we have a floating point value of some sort. So I'm going to show you how you use type arrays to be able to define that particular structure. First of all, I have preloaded a buffer called right here with these particular values. This is on purpose here to give me a set number of values within the data. So what I've done now is I've gone to my header, and within the header itself, I am now using type arrays to be able to say I've got a 16-bit array to begin with. That's the unsigned word. Then I have an unsigned 8-bit array. That's the unsigned byte. Then I have a signed 8-bit array. That's the signed byte. Then I have an 8-character string. That's the title character here, and then I have a 32-bit float at the very beginning. So the real key here is two different things that's kind of different from what we did last time. Is first of all, notice that our byte offset has changed each and every single time. First one starts at byte 0, the second one at byte 2, the next one at byte 3, the next one at byte 4, and the final one at byte 12. Also, I went on ahead and just grabbed the first element of the array because I just happen to know, we're going to be creating an array here. Even though we're just getting one item, you can tell by the length of 1 here, we're just getting one item. We don't want to have return just the array itself. We want to return the actual number. So I'm going ahead and extracting the first value. The only thing different I've done here is on the string. And this shows you a very quick and easy method to be able to change an array buffer, a section of an array buffer into a string. I first of all turn it into an unsigned 8-bit integer with where the byte offset is with the length of how many characters, because we do have 8 characters in the title. So with the length of 8 characters, I change that to an unsigned 8-bit binary array. And then I'm using the from car code method to be able to convert that array into a character code. Real simple, really quick, works like a champ. And this will convert everything that's within that array into a string. So this is my header. I've got my signature, my 2-byte signature, my 1-byte status, my 1-byte weight, my 8-byte title, and my 4-byte value. Let's see how it works. Let's flip over to Node and type in node structure. Yep, there it is. There's my signature, my status, my weight, my title, A, B, C, D, E, F, G, H, and my value of 762.119991, whatever that happens to be there. So this shows you how you're able to combine a number of these particular typed arrays to be able to get you a structure. But there's a major catch. And it's a really big one. I'm going to show you that next. So now let's take a look at a real-life, real-world example of how to use typed arrays to map out a structure of a binary data stream. I have here the local file header structure of a zip file. Now, if you're not familiar with zip files, it's basically a way to take a whole bunch of files, compress them down, all into one single file, and that single file is sent over to somebody else where they can uncompress it and have all of the files available to them. It's a nice, convenient, easy method for transferring files from one computer to another. Now, with a zip file, you have all the files themselves have been zipped up at the very beginning, one right after another, and then you have what we call directory structure, which describes the directory structure itself. So what we're going to do here is we're going to sit here and have a little program to be able to read out all the different files that are at the very beginning, and then once we hit that data structure, we're going to stop our processing and say, okay, here's a listing of all the files. We're not going to do any uncompression or anything like that. We're just going to get a listing of the files. So all I care about are the file headers, and I can see here that I've got a 32-bit array, 4 bytes is 32-bit. I've got a 2-bit, which will be a 2-byte, excuse me, which would be a 16-bit array. Another 2-byter, another 2-byter. Here's a 4-byter for the CRC, another 4, another 4. Here's a 2-byte for the file name length. Here's a 2-byte for the extra field length. And then I got the file name and the extra field. So in my file entry itself, what I've done is I have gotten the header to be able to give me the first 32-bit array, because that will match the 4-byte word here. Then I've got the 5 other 1-bit arrays, or excuse me, 2-byte arrays, which would be the version, the bit flag compression method, the last mod file time, and last mod file date. That will represent these 5 right here. Then I have the CRC, the compressed size, the uncompressed size. That will represent those 32-bit arrays will represent those 3 right there. And then I have the file length and the extra field. And then on the file name here, if the file name length is actually there, then I grab that data and convert it into a string. If the extra field length is there, I grab that data and just store it, because I don't know what that's for. And then I set numbers with the data offset and the file offset to be able to, at a later point in time, with the program who is consuming this, be able to say, okay, this is taking up this number of bytes, so the next one you want to get is going to need to start at this new point. And that comes in handy in our zip file. This is the file we're going to run. And in the zip file, I've got a zip where I've zipped up one of my older class lessons that has 4 different files in it. And then I'm just going to do a quick loop while done. As soon as I get to the central directory structure, I know that I've finished all my files, and I'm going to say I'm all done. Otherwise, I'm going to push the new file entry and restart the start. And the start number here is going to change with each and every single file entry. So that will give me the ability to say, here's a group of files with maybe 400 bytes. Here's another group that has maybe 600 bytes. Here's another group that maybe has 1,000 bytes, and so on and so forth. And then I'm just going to list it out here saying name, compressed size, all that kind of fun stuff. So you want to see how it works? Of course you do. Let's go over to Node and type in node zip. And so we should get our for no. So what happened here? Well, this is the big bugaboo. that you're going to run into with type arrays. Notice this error message here. Start offset of uint32 array should be a multiple of 4. Whenever you're using type arrays, it's going to want to be able to align itself to within the buffer of how big it's going to be. So if you're going to be using uint32 arrays, it's got to start at bytes 0, 4, 8, 16, 20, 24, 28, 32, and so on and so forth. uint arrays, we're going to want to start at 0, 1, 2, 3, 4. U16 arrays are going to want to start at 0, 2, 4, 6, 8, and 10. If there's any number besides that, it's going to throw an error. So it's always got to be on a 4-byte boundary. And notice start plus 14, the very first time through, start is 0, so it's going to start at byte 14. Well, byte 14 is not on a 4-byte boundary, so it's going to blow up on you. So how do you fix that? Well, let me show you how you fix that. Actually, 2 different ways to fix it, the hard way and the easy way. So let's go and do the hard way first. I've got another program here called file entry that does the exact same thing here, but what I have done now is I have written 2 particular routines here, one called toUint32 array and toUint16 array. Because the idea here now is what I'm going to do is I'm going to take the array, I'm going to take an 8-bit array of however bytes it is, and then I'm going to pop it into a new buffer. And when I set it to a new buffer, that means I can get the byte offset of 0. So the idea here is that let's assume we have that 4-byte that starts at byte number 14. Of course, that's illegal. I'm going to then move it to a new buffer where it starts at byte 0. I'm going to convert that and then send that back on to the calling program. So basically, I am able now to, by doing it this way, I am able to convert to a 32-bit integer or a 16-bit unsigned integer any placement within the array simply by moving all that data to a new buffer and then returning that. So with every one of these functions, and I've made these as static functions, every one of these functions here, I am, first of all, I'm creating the uint8 array for the exact size. I'm going to need 4 bytes, 2 bytes, 2 bytes, 2 bytes, 4 bytes, whatever. And then I'll convert everything to a uint32 or uint16 array. And that will give me the ability to now be able to map all of that into those particular arrays. And the same thing down here with the string code and all that kind of fun stuff. So if I go back over to zip, instead of just saying file name original, I'm going to now point to my file entry itself, and we'll save it. If I go back over now to node, let's clear the screen off. Let's run zip again. And there we are. There's my 4 files. The blank file, the classless CSS, the HTML, and the JS, and their particular compressed sizes. So I said there are 2 ways. That was the hard way of doing it. What's the easy way? Well, quite honestly, the easy way is not using type arrays. There is another method that was created just after type arrays were created called data views. And data views allows you to be able, basically the same thing here, but to be able to map any of these things, 32-bit, 16-bit, 64 bits, into any position within the buffer. Now, we're not going to cover data views in this video. We're going to cover data views probably that first week of September or something like that. But I want to kind of give you the idea here is that there are some limitations of using type arrays to be able to map out data. As long as you're on those boundaries, you're in great shape. If you're not on those boundaries, you've got to do some manipulations like you see on the screen here. So again, type arrays are wonderful for being able to map out the data on your binary stream, but there are some gotchas you need to be aware of. And that's all there is for using type arrays. I hope you enjoyed our video. Hope it didn't bore you to death. Please view all of our videos at www.boringjavascript.com. Subscribe to our YouTube channel or check out everything we have at www.thevirtualoid.com. Thanks again for watching, and we'll see you later.